All right, there we go. So earlier today, welcome back everybody, I downloaded Homework 1 and updated grades. So if you log into the homework portal, if you were able to complete the assignment, you should see all the points you accumulated. And you should see green text for all the answers that are correct and red text for anything that is incorrect. If you look through your work and you're not sure why you got something wrong or what you should have done, please let me know and I'm happy to clarify, but you should at least be able to see your work. Not everybody has finished it, so that's not something I can go over as a group, but if you have questions, let me know. If you weren't able to finish it, no worries. You can submit late work at any point throughout the semester. It's 1 point off for being late, and that's it. And if you did homework 0, you already have 2 extra credit points, which translates into 2 free late assignments with no penalty. So no worries on any of that. And we have lecture 2 and example 2 for this week. The next thing that you'll have to do is formative assessment number 2, which is not yet posted. I was waiting to see how far we got, so I can make sure that the questions that I ask are answerable this time, having learned from my last mistake. Trying to post it too early is not a good thing all the time. Any questions, logistics, schedule, before we dive back in? No?
Lisa, can you?
Yeah, go ahead.
Can you tell us if, like, for, I think you said this about homework, but also for formative assessments, like for next week's, we can start on it already because it's on last week's material? Is that right?
It will be on last week's material and this week's material, but it's not ready yet. So I will probably put it up either later today or tomorrow. I had wanted to make sure that we're going to cover everything. But it'll be the same deal as last time. Short answers to quick questions. It shouldn't take too long. It's mainly an opportunity for structured review for you, but also a chance for me to check in with everybody. And if there's any common misconceptions or confusions, if there's questions you want to ask, like about whatever the questions are, it's just a little bit of a chance for us to interact in that way. So that is not quite ready yet, but it will be soon. Okay, anything else? All right, then have I started screen share yet? Zoomers, can you see my screen? Okay, I did that part. In this process, there's like 17 things I have to get started for it to work properly, and so I sometimes forget where I was in the process, but I did that part already. That means that I can put up some PowerPoint stuff. We can talk about what we remember from last time. So where we were last time was talking about hypothesis tests and how we decide how to talk about the results of a model with one predictor. So for instance, let me see, maybe this. Maybe one further. Yeah, let's start here. Let me do this slide again. I like this one. I'm on slide 27. So this slide is kind of busy, but hopefully it will help visualize what we're trying to do. So we're trying to predict a quantitative outcome. And right now we're predicting it from either nothing, which is called an empty model, no predictors, or one quantitative predictor thus far. So the example data that I'm playing with, the outcome variable is annual income in thousands of dollars. And I will show you, by the way, where all of these numbers came from. We're just talking about the concepts of what they represent. How to get SAS data RR to give you the numbers is then a separate process. And so we will get to see all the numbers again in that context in the example. So the average income for this sample is 17.3. So in my empty model, that is what beta 0, my fixed intercept, becomes. If I don't know anything else about a person, my best guess for what their outcome variable will be is the mean of the outcome for that sample. For this particular individual right here, we're trying to predict their outcome. The mean of the outcome variable, as given by this purple line prediction here, is not a very good guess. It's pretty far off. Their residual, so E sub I, is an individual specific residual. Their residual is 41.5. And if I figure out what the residual is for each person, so Y sub I, what they got for real, minus this thing here. Do you remember what this little thing is? What's this thing called? Hat. Yes, y hat. That thing, blow it up a little bit. What's y hat a placeholder for? Yeah, it's what the model is predicting. So at this point, y hat is the same as beta 0 because there's nothing else in there. So it's a placeholder. Y hat is the idea of, based on your predictor information, what should your outcome be? So then what you actually got is y, minus what you were predicted to get is y hat. That's the same thing as e for the difference. E is how far off your outcome is from what's predicted. In an empty model, the variance of the e's is all the variance, which is 190 for this example. We then added a predictor for years of education, and that variable is centered. So the term centering, another vocabulary word, that means we have rescaled the predictor so that 0 is a meaningful value. There's no wrong choice as to where to center, but there are weird choices. So in this case, because this is years of education, and because this is a US sample, I picked 12 years because that means a high school degree. So now my model to predict annual income is this part right here. Beta 0, that's my fixed intercept. It changed from 17 up here to 14 down here because it means something different now. 14 is the expected outcome when education is 0, which in this new scaling corresponds to education of 12. So at 0 on the x-axis down here, 14 is the spot on this blue regression line, right there. See, if I move it, then it's easier to see. This spot right there. The slope of this blue line is conveying the slope of 1.8. So for every additional year of education, annual income is predicted to go up by 1.8. For this person that we're predicting this for, they have 8 additional years of education beyond 12. So their model prediction is this 28.4. So for this particular individual with 8 years more education than high school, their predicted outcome is 28.4. Their y hat is 28.4. So that gives me this spot right here. Now that's better. It's closer to what they actually got, which is way up here, but it's not there yet. So then E fills in this remaining gap. The residual is how far off from the regression line each person's outcome still is. And if this predictor is useful, what we should see is that collectively everyone's E's should get smaller. And indeed they do. The variance of the E's across people is down to 162, and it started at 190. Okay, so that's just a little bit of review. Any questions on any of that before we move on? So these numbers are what they are. These are the values that collectively make the E's from my sample the smallest. In terms of stat words you may have heard before, this idea that the right answers for what the intercept and slope should be are the ones that make the E's the smallest. Another way of saying that is that this is the solution that minimizes the sum of squared error. So this term right here, sum, there's my sigma, of squared, that one, to keep the positives and negatives from canceling, the interior is error. So that's where these numbers came from. Mathematically, they are the way to guarantee that the set of E's is the smallest possible. But it's a different question that we still have to answer as to how good they are. How likely would we be to get these same values if we were to repeat the study in another sample? How inconsistent would these results be across samples is something that we don't yet know, but something that we do need to know. Standard error is a way to quantify that. So given the values in this example, the standard error for the slope works out to be 0.16. So definition time, standard error, is always how far off the sample whatever is on average from the population whatever. Where to fill in whatever, it's the thing you're estimating. So in this case, this standard error tells me how far off on average a sample slope is from the population slope. If I'm talking about the standard error for the intercept, which works out to be 0.55, then that tells me how far off on average the sample's intercept is from the population intercept. So standard errors index inconsistency across repeated samples of the same kind, even though we only have one. That's the crazy part. So let me give you a free homework answer. If any of your choices is ever, this is the population something, that is the wrong answer. I'll just tell you that right now. Because the population is a hypothetical construct that we do not have. Because guess what? If I knew the right answer in the population, I wouldn't need to do research. I just know. So the only way you know what the population answer is if you make it up in the data, like I did for demonstration purposes. We never know what the right answer is. But nevertheless, because math, we can anticipate how inconsistent our results would be across repeated samples. So the things that make results more inconsistent are the ingredients of the standard error. One of them is right here, residual variance of y. This thing, sigma squared sub e. Conceptually, that is all the reasons why people still differ from each other that aren't in your model. That's what residual variance means as a concept. It's the variance across people of the e terms at the end of your equation that capture how bad your model is. And guess what? If your people differ from each other more, then your results are going to be more inconsistent across samples. If people differ from each other less, then your results will be more consistent across samples. So smaller residual variance means smaller standard error. Likewise, this term right here, n minus k, what's n again?
The number of subjects.
Yep, number of subjects, sample size for one sample. What's k? And feel free to read from the slide. K is an abbreviation.
Beta 0 and beta 1
That's right.
are K.
Yep. K is an abbreviation for the number of fixed effects. A fixed effect is a general term for an estimated constant. Beta 0 is a fixed intercept, that's one. Beta 1 is a fixed slope, that's the other. So the more people that you have, does your standard error go up or down? Down. More people, more precision. More people, more consistency. More people, less noise. Is 2 fixed effects the same as K? Yes. Number of regressors. Good question. No. Number of regressors is number of predictors. So across different textbooks and notational systems, they may say that K is the number of slopes or K is the number of fixed effects. The way I do it is that it's the number of fixed effects. Regressors is predictors, which is X variables that predict your outcome. Okay, question in the back?
Yeah, it's K always a binomial, always has two effects.
Nope, in this model there's two. So if I add in, what else do you think relates to how much money you make besides education? What kind of job you have, maybe? So if I put in another predictor for what kind of job you have, then I would have a beta 2 that goes with that, and then I'd have K equals 3. The way that you can think about why that matters is that this n minus k it's reflecting like, okay, how many things did I have to know to get to this level of leftover variance? It's contextualized by the complexity of the model. So models that have more predictors that don't do a better job are not as good. The principle of parsimony. So we kind of penalize by keeping track of this k. But in general, more people, smaller standard errors. Okay, how are we doing? So now we've got all the ingredients that we need to do a hypothesis test. And I think that was where we ended up on Thursday, is starting to talk about null hypothesis testing. Does that ring a bell? Because the number one question that people want to know when they put a predictor in the model is, did it help? By how much did it help? So did it help is a binary decision, yes or no. How do I know that? Well, let's define what help means. What's the worst you could do with respect to a predictor? What is the worst slope you could have if a predictor truly doesn't matter at all? 0, flat line. So a starting point for, okay, does this thing matter? Is it 0? Well, I don't know, like it's 1.8. That looks like not 0 to me. But I'm just eyeballing it. Now this thing right here, standard error of my slope, that tells me how far away on average is any one slope from the right answer. So if the right answer were 0, how far away is 1.8? A lot. If the right answer is 0, we would not get a slope this big if the average deviation of a slope from the population is only this small right here. So putting numbers on that, this is slide 33. We're talking about comparing our slope to some expected amount that we use to judge it against. You can pick whatever number you want. In the context of most research studies, the null hypothesis, so that's HO right here, is that the slope is 0. Doesn't have to be. Have you guys heard the term meta-analysis before? Or research synthesis, those words? So the idea of pooling multiple studies with each other that are all about the same thing to try and get a better estimate of what happens. So let's say that I have a meta-analysis available to me where I have several different studies that have looked at the links between annual income and education, and their best guess was that the slope should be 2. Now, if I wanted to compare my study to sort of the going rate of 2, I could do that. Then my null hypothesis would be 2, and I would test how different 1.8 is from my expected null hypothesis of 2. Or 3, or 12, whatever. 0 is what it is most commonly, doesn't have to be. But the reason that it's 0 is because that is the value that corresponds to absolutely doesn't matter whatsoever. Flat slope. So does it matter, yes or no, is the decision that we're headed to. The path that gets us there is to use the estimate of the slope, the 1.82, the best answer given our data, and its standard error to compute what is called a test statistic. And at this point, the transcription of Zoom usually mumbles it into somewhere around fish stick or something like that. So test statistic is difficult to say even without a mask on. So this is just going to be like t-value. That's what this number is, this value, this terminology is going to change to very quickly because test statistic is a mouthful. But how you form this test is the numerator is, okay, so how far off are you from what you thought should have happened? I got a slope of 1.82. I thought it was going to be 0. Okay, I'm off by 1.82. What if I thought the slope was supposed to be 1? Then how far off am I? If it's supposed to be 1, then I'm higher by 0.82. So the numerator of this test statistics, its purpose is to say how far off are you from expected, whatever expected is, okay? Now standard error, is a way of conveying, okay, well, how far off should you be on average? What is expected offness given the behavior of this statistic? Well, in a sample size this big, with this much leftover variance, we just found that that standard error for my slope is 0.16. So if I redid this study, I would expect my 1.82 to be off from what it's supposed to be in the truth. We don't know what the truth is, but that doesn't stop us. It would only be off by 0.16. So the ratio that results of estimate minus null hypothesis divided by standard error, this test statistic is this ratio, 11, is saying that I am off by a magnitude of 11 relative to what expected fluctuation would be. $11 is a lot. I'm off by a factor of 11. So yeah, this definitely looks like I can say, you know what, 1.82 is not 0. Because I only would have been off by 0.16 on average, and I'm off by 11.16s.
Question.
Yeah, hit me.
Can you review the difference between like the t-value and the standard error? Like, I'm not sure I'm understanding that.
So T is going to be what this thing is called.
Okay.
This number, this test statistic ratio number, is either going to be located on a T distribution or a Z distribution. And Z doesn't work for small samples, so it's going to be T. Standard error is the ingredient. Stop it. Standard error is the ingredient that forms the denominator.
Okay.
So estimate and standard error are the two things that you need to get to everything else.
Okay. Estimate and standard error to get to the t-test, the
That's right.
t-value.
Yep. This is a test statistic that is going to form our t-test or t-value or whatever, t.
Okay.
Yep. It's convenient that T stands for test. There's a mnemonic for you.
Thank you.
Sure. So the job of this is to create a standardized metric for how far off we are from what we thought we would get. Where the numerator is how far off from expected, the denominator is, well, how far off should we be just kind of like due to random fluctuation? And so how much worse than that are we? How much farther away from expected are we? And all these numbers are going to show up in your output automatically. You're not calculating a single one, okay? And in this class, we're working with a two-sided alternative hypothesis, meaning that we will accept a result because it's either too far away in a positive direction or too far away in a negative direction. Either one of those is a valid possibility. Okay. So this then, I think, is about where we ended up. This is slide 39. This is a t probability distribution function. It is the way that we are going to judge just how far away from expected we are. The job of any of these shapes like this is to give us an expectation for how frequently a given result would occur. So here's the normal curve. It looks pretty much the same. This is a different distribution that's taller in the middle, but it tells us that 68% of the time you should get results within plus or minus 1 standard deviation. So in our context, that would be plus or minus 1 standard error. So our 1.82 is expected to differ across samples by 0.16 on average. So that means that we would only be within about plus or minus 0.32 most of the time. 2 standard errors 95% of the time. 3 standard errors 99% of the time. Now, where exactly those percentages fall depends on your sample size. So this is actually not a good indicator for most fixed samples, and that's why we have our friend t. So where the unexpected area starts depends on your sample size. So here's the picture where I'm headed to, and this is new, and I have some practice with this. So this is a busy picture. Let me walk you through the pieces of it. The x-axis here, the bottom, this is in units of t. So t equals 0 if you are exactly where you thought you should be. If my null hypothesis is 0 and I got a 0, then t is 0. Or if the slope that I thought I was going to get is 2 and I got a 2, then I'm at t equals 0. So 0 means you got it exactly right, what you thought was going to happen. Now each of these niche thingies, what are these things called? It's not, niche isn't quite the right word. What's the word I'm thinking of? Was it natch? What is it?
Nut?
Not nutch? These things. These little tiny line things. I'm out of words. Yeah, it's somewhere close to niche, but that's not quite the right word. Notch. Thank you.
Oh, there we go.
I'm off by a vowel. Notch. Yeah, this is a notch. That's what I was going. Each of these is 1 standard error. So this is standardized such that a standard deviation is your standard error. So then we have these boundaries out here that we use to decide if our given result is too far away relative to what is expected. The area that we allocate to unexpected is your alpha level. Alpha is how often are you willing to be wrong? If I'm going to flag this as unexpected, this is not what I thought I would get, this is noteworthy, I'm going to write this up and try to publish it, how often are you willing to be wrong? Said differently, what is your false alarm tolerance? Standard choice for that is alpha of 0.05. That means that you are willing to be wrong 5% of the time, and 2.5% of that is willing to be wrong because it's too high in the positive direction, and the other 2.5% is willing to be wrong because it's too low in the negative direction. So in my story, I have a slope that's positive. It's 1.82. What is my null hypothesis for the slope? In my story, it's 0. How many units away from 0 am I in standard error units? The math for that? 11. I am 11 standard errors away. So in this picture, I'm clear out here on the right-hand side. Because this is 2. The green line is 2. So 11 is like on the other side of the classroom from here. So I'm definitely in unexpected territory. And I can actually ask the software to tell me just how unexpected, which is my exact p-value. But because I set up my test to say, you know what, I expect a 0. If it's 0, then it means it doesn't matter, and I want to know if it matters. And I'm willing to say that matters means that it would be a positive slope or a negative slope. Then I've allocated my unexpected region to both sides. And that's where the term two-tailed test comes from, is because this section of the distribution at the end is called a tail. So there are only 4 possibilities with respect to the decision that you make, how you would talk about the result that you got. If you are in unexpected territory, so you are beyond where 2.5% starts on the right-hand side, then I would say that your slope is significantly positive. Significant means would happen less than 5% of the time if your null hypothesis is true. Sufficiently rare is a synonym for significant. And in some other intro stat class, that would correspond to reject the null hypothesis. Reject the null hypothesis, unlikely to have happened due to normal sampling fluctuation. It is significant, statistically significant, specifically. And because it's a positive slope, then I would call it a significantly positive slope. Now, what if it was a positive slope, but it didn't make the cutoff for where 2.5 starts? Then I would call it non-significantly positive. So in your second homework, you will get a chance to practice with these vocabulary words. You will have a drop-down box with like these 4 choices in them. And I'm looking to see that you can locate a slope on this distribution given how far away it is from 0 in standard error units. So let's say that our slope was like 0.3. It's positive. A 0.3 slope would mean that income is predicted to go up by 0.3 for every additional year of education. But 0.3 is not 2 standard errors away. It would be close. It'd be like right here, because our standard error is 0.16. So anything that falls within this territory right here, I would call it non-significantly positive. It would happen more than 2.5% of the time. So it's 2.5 on either side, which is why it's p less than 0.05. Likewise, if we had a negative slope that was, say, negative 0.3, then I would call that a negative slope, but it's not far enough away to be classified as unexpected. And any slope that is far enough away on this other side would be significantly negative. So the sign of the slope tells you positive or negative. The sign of the slope relative to the null hypothesis then dictates where t is. For a null hypothesis of 0, the sign of your slope and the sign of your t are the same. Then the significant or not, you are literally going to get a column on your output that tells you exactly what p is. If p is less than 0.05, it is significant, reject the null. If p is greater than or equal to 0.05, it is non-significant, do not reject the null. Okay. I've been doing a lot of talking. Your turn. Any questions? You want to practice? To Excel.
I have a question.
Yeah, hit me.
Okay, so with that, the graph of the standard error, so hang on, let me see where I'm at, negative. So it no longer corresponds now with the positive slope being to the left because now it's non-significantly negative. So now the word negative is on the left.
Negative is the left-hand side because the center is 0. Yeah, the center in this case is 0 because the null hypothesis is 0, but what 0 means is, what did you expect?
Okay.
So T is all about a standardized deviation from what is expected. So let's do some practicing. Okay. I have a couple scenarios here. This column, HO, what's that? Vocabulary drill. What's HO represent when you see those two letters? Null hypothesis, yeah. And I think that, I don't know if I put this as a 0 or the letter O, but it should be 0. Null hypothesis, yep. Slope estimate, that is our best guess using the data as to what the change in Y per unit change in X should be. Slope standard error, that is how far off, on average, a slope is going to be from the population slope across samples. Expected inconsistency. So I just made these numbers up. I made them up because the math is then easy. But Excel is doing the math for me. So these 3 columns, that's all I need to know. The rest falls out. So T, that is my test statistic, otherwise known as t-value. T is my estimate minus the null hypothesis for it, divided by standard error. So I have that programmed in here as a formula. 6 minus 0 divided by 2 gives me 3. So 3 tells me how many standard errors away from the null hypothesis my slope is. If I have 10 people and 2 fixed effects, an intercept and a slope, then n minus k, or what is going to be called denominator degrees of freedom, is 8. That dictates then the exact shape of this curve, how flat it's going to be. So 1 second here, let me get a picture up for a comparison. Where did my T's go? I lost it. This, here it is. This shape, how flat it is. 8 means it's going to be relatively flat. The black line is what it would be with infinity sample size. So there is a function inside Excel that tells you exactly where unexpected starts. So in my picture here, I have 2-ish labeled as where unexpected starts. It's going to be somewhere close to 2. Unexpected is where you would find a result beyond that line less than 2.5% of the time on the positive side and less than 2.5% of the time on the negative side. So we have carved up this distribution into 4 regions. Unexpected positive, expected negative, and unexpected negative. Where the dividing line is located is a function of your sample size. So look down here, this line versus this line. Unexpected, if I had 500 people instead of 10, starts at 1.965. And you do not have to know this or memorize this. The computer will tell you exactly which t-distribution you use for your result. It's programmed in. So if I go up here, my exact p-value, this is a column that will show up in your output from your programs. How often would I find a slope this many standard errors away from the null hypothesis if the null hypothesis were actually correct in the population? If my null hypothesis is 0, so my benchmark of does not matter, slope is 0, and I got a 6? 6 is a lot bigger than 0, right? Ah, wait. What could I have gotten? Well, the standard error is 2. So in any one group of 10 people, that 6 would have a wiggle on average by plus or minus 2. So I got to temper my enthusiasm. So another way of saying that is that my obtained slope of 6 is 3 standard errors away from what I thought it should be. That makes it to the unexpected side, this area right here. A slope of 6 would only be obtained 1.7% of the time if the right answer for what it is in the population is actually 0. So because p less than 0.05, that's the first word, significantly. And do I say positive or negative? What was it?
Positive.
Positive, yeah. And how do I know that? The slope is 6. It's a positive number. It's not any harder than that. Okay. So I'm over here. All right, with me so far? Now how about this one? I got a 6 again, but this time my sample had a lot more variability in the outcome. The 6 is not as effective because my people are more spread out. So that additional variability caused my slope standard error to be 3. Now, my slope of 6 is only 2 standard errors away from what I thought it was going to be. So 2 is less than where unexpected starts. Where unexpected starts is your t critical value for this test. Critical means the line you have to jump over to get into unexpected significant territory. So this is like a high jumper. They're carrying the pole, they're running, they plant, they throw their body upside down to get over the pole, and they just don't make it. They're off by like this much, and you're like, oh. That's what a p-value like this is, 0.08. So what's my decision about my slope of 6? Non-significant. Significantly. It's still positive, it's still 6. But it's on this side now. It did not cross the bar of 2.3 as where unexpected starts. In other words, if the true slope were 0, I would get a slope as big as 6, like 8% of the time. Not unexpected enough for me to say, yeah, it's different than 0. It's not quite different than 0. Because null hypothesis testing is about making a binary label as to whether or not this is different than expected or not. And the answer here is not. Not significant. Do not reject. I could have gotten this 6 based on normal sampling fluctuation because in this result, my slope is going to be off from what it's supposed to be by 3 on average. I could have lucked out with the 6. Okay, with me so far? Now, when you see this reported in papers, has anyone read research papers using quantitative methods where they have p-values that are just not quite significant? There are 8,000 euphemisms for this type of p-value. Marginally significant, almost significant. My personal favorite is approaching significance because it makes it sound like a cake that's just not done baking yet. Like if you check on it later, it's going to be significant, it's just not there. So you'll see all kinds of euphemisms for marginal significance. Now, what if we do the exact same two scenarios in a larger sample? Slope of 6, standard error of 2, same decision, because p less than 0.05. In this sample, my slope is 3 standard errors away from expected. That puts me out here into unexpected positive territory. What's the difference? Yeah, sample size moves the goalposts. The more people you have, the easier it is to hit unexpected territory. The more people you have, the more consistency you would expect in your results across samples. The more people you have, the further in the goalposts are for where 2.5% starts on one side and 2.5% starts on the other. So in a sample of 500 people, this slope would happen less than 0.2% of the time if the true null hypothesis was correct, if it was really 0. Now what about this one? If I compare those two, what's different? Sample size. Sample size moved the goalpost. More people, more power. More people, more consistency. So now this same result that was non-significantly positive up here in a larger sample would be classified as significantly positive because p is less than 0.05. So in practice, these are the 3 things you need to know, and everything else is a consequence. Software by default uses a null hypothesis of 0. If you want to change it, you have to override that. It'll tell you what the estimate is. It'll tell you what the standard error is. Based on those two, estimate over standard error gives me t. The number of people that I have and the number of fixed effects in my model gives me denominator degrees of freedom. Denominator degrees of freedom tells me where my boundaries start, where unexpected starts. And they also then tell me exactly how often a result like that would be expected if the null hypothesis were true. That is what a p-value means. All right. The other ones. Let's do number 4 here. Slope of -6. Standard error for it of 2 gives me a t of -3. Note the sign is the same. It has to be. If the null hypothesis is 0, then the slope of the sign and the slope of your t ratio using that estimate is going to be the same. Note the p-value is exactly the same for a t of 3 as for -3. They're symmetric. So for this row right here, slope of -6, standard error of 2, that means that I am 3 standard errors lower than I expected to be. Does that cross my line in the sand? Yeah, the line in the sand is 2.3 if I've got a sample size of 10 and 2 fixed effects. So what do I type here? Significantly negative. Last but not least,
Non-significant.
this one's non-significant, and how do I know that?
Because the t-value is different, it goes, it's a -2.
Yep, t is within the boundaries. And more directly, the p-value is greater than 0.05. So this would be a non-significantly negative. So this column right here, I'm guessing that if you've done this sort of thing before, like if you learned how to do a t-test, this is the column that was in the back of your textbook that you had to look this shit up. We don't have to do that anymore. This is hidden from you. You won't ever see this in your output because you don't need it. What you will get are basically those columns and the p-value. The p-value is a way of judging essentially how far away from your barrier you are. So all you need to know is the sign of your slope and the p-value, and that's your decision. Question?
So my p-value depends on my alpha?
No. Your p-value depends on how far away from expected you are. Whether you label that significant or not depends on your alpha. So let's do that. What if you decide that you don't want to be wrong that many times? If you want to be more conservative, if you want to have fewer false alarms, what might be a more conservative alpha to pick?
0.01.
0.01? Does that sound good?
1%.
Yeah, 1%. So let's switch it up. Let's change my alpha to 1%. Now, in this case, I'm going to need a new column. Okay, inside this formula right here, the reference is all moved over, so let me fix that real quick. Hey, 1 second. Copy. Nope. And you see now why I build these things ahead of time. There we go. Now, inside here, it's set to 0.05 is where unexpected starts. Inside the t function, I'm going to change that to 0.01. And now I need to refer to, no, this one here. All right. Anywho, I think you can see what happens even if the alphas aren't going to change, or the p-value is not going to change. Now where unexpected starts has moved. Unexpected starts at a t of 3. So these p-values are no longer, actually no, never mind, they are correct. This is why I don't do things live very often, because I talk myself out of things. But these p-values are correct. The decision we make is different. So if we're holding ourselves to a stricter standard of 0.01, what is my new conclusion about that number? If my cutoff is 0.01 and my obtained p-value is 0.017, then am I less than 0.01? Yeah, this rounds to 0.02. So I'm no longer significant. I'm going to abbreviate non-significantly positive. In other words, the exact same thing happened. Those values are the same. I am 3 standard errors away from what I thought, which it should only happen we'll call it 1.7% of the time. We'll do it that way. But I have changed the barrier for where unexpected starts to 0.01, so it's not significant by that standard. Question from the chat. What if our null hypothesis is 2 and our slope is 1.9? So it may be left of the null hypothesis, but also positive. Would we call that non-significantly positive since the slope is positive, or non-significantly negative since it is to the left? Oh boy. In that case, because of that ambiguity, I would phrase it differently. So if I think I can enter that situation here. If I have a 2, and let's say that my slope is 1.9. So in that case, my t is negative because I'm lower than I thought I would be. So I would phrase the decision in that case as my slope is less positive than expected. So if I thought I was going to get a 2, and I got a 1.9 instead, that's still a positive slope. It's less positive than expected. But because it is less than expected, that translates into a negative t. Okay. Having a null hypothesis of 0 is convenient because then you don't have to pay attention to that. A positive number is just positive. But it really, what we're talking about is more positive than expected. And if expected is 0, then it's simple. Okay. 301. How are we doing? Okay? So one thing that we haven't talked about in any of this is how to qualify how big of an effect this is in a absolute sense. Because as we've just seen, the decision about whether a given effect is significant depends on your sample size. It depends on the alpha, where you set the barriers for where unexpected, what % you're willing to be wrong. What we also need, which we do not have yet, is a measure of effect size. The term effect size means a translation of your results into a standardized metric where everybody would look at that number and go, oh yeah, I know exactly what that means. Because in order to know what a slope of 6 means conceptually, I got to know what the units are of x, I got to know what the units are of y, I got to know my sample size and my standard error to know if it's significantly different than 0. Those are decisions about the significance of the slope relative to expected. What I also want to know is kind of how big it is in an absolute sense. So eventually we need to pick up something with effect size, and I need to see if that's what's next or if I'm headed in a different direction. I did head it. It's like 4 slides from now, so I'm getting a little bit ahead of myself. Okay. Are we ready to move on, or are there any other questions on this idea? Okay. Then there's one more piece of output that I haven't introduced yet because I kind of hate it, to be honest. Confidence intervals. I know. I put it out there. I have opinions on a lot of things that most people do not. I hate confidence intervals. I don't think they actually tell you anything that's helpful. That's my opinion. But guess what? You can build them out of your estimate and your standard error. The same two ingredients make these also. A confidence interval is, and I have the definition here so that I don't get it wrong, it is the interval predicted to contain the population value in 1 minus alpha % of repeated samples. So alpha is the inverse of confidence. So if alpha is 0.05, then you would have a 95% confidence to go with that. Confidence is like expected territory. And one of the reasons why I don't think the confidence interval is very helpful is that it tells you the same thing as the p-value with respect to your binary decision. If your confidence interval crosses HO, then it's not unexpected. It's expected. If it doesn't cross HO, then it's unexpected. So it's the same exact binary decision that your p-value relative to your alpha is. So here are what confidence intervals would be for our slope in our example. So our slope was estimated at 1.82. That's the best guess for what it should be from our data. 0.16 is my standard error. That tells me how far off on average my slope is going to be from the population slope across repeated samples. And in this data set, I had 734 people. I had 2 fixed effects, an intercept and a slope. And so my denominator degrees of freedom are 732, which is functionally the same thing as the z critical value. So at here's my little picture. Here it is. I'm at the black line. So if you get enough people, T morphs into Z, and you can use those dividing lines for your area that are sample size independent. And here I was. So the areas, this is slide 42, make that big. The area where unexpected starts, that's your critical value. So that's what's in the colors here that correspond to the parts where the dividing lines are on the standard normal distribution. So if I want to make a 90% confidence interval, then it's 1.65 as my where unexpected starts times the standard error. If I want a 95% confidence interval, then the benchmark on Z or T at this level of degrees of freedom is 1.96, and 99% starts at 2.58. So these intervals here, if you see them in a table, the first number would be called a lower bound, and the second number would be called an upper bound. They characterize the interval predicted to contain the population value in that % of repeated samples. So it's a way of making the amount of expected inconsistency more direct. And so putting it all together, what's in your output and what you would need to report in a results section for a manuscript, for a thesis. Estimate and standard error are the two things that have to be there. Everything else is a combination of those two ingredients. So you will see in your output columns of a table starting from the left where the estimate is provided. The standard error of the estimate is next. Estimate divided by standard error, that gives me my t-value, my test statistic for how many standard errors away from expected I am. Denominator degrees of freedom, that is sample size minus the number of things you had to know basically to get to this level of prediction, k for the fixed effects. P-value, how often you would find a result that extreme if the null hypothesis were true. And then a confidence interval, which is based on your estimate, your standard error, and your alpha level. This is also known as a univariate Wald test. If you don't use denominator degrees of freedom, then you would treat this as a Z test statistic instead of a T. All right, questions? Hit me.
Can you explain again about the lower bound and upper bound in the computer nature?
Yep. So this confidence interval is telling you basically where expected fluctuation would be. It's roughly 2 standard errors on either side of your estimate, but the roughly 2 is based on just how confident you want to be. So if you want to be very confident that your interval contains the population value, you would pick like a 99% confident, and that interval is much wider than if you picked, say, a 90. Yep. All right, other questions? So then putting it all together, for our example, our slope of 1.82, given its standard error of 0.16, is 11 standard errors off from expected, definitely positively significant. And the way that I would write that in a paper or something like that would be, predicted income is significantly higher by $1.82 thousand, so that's my slope for each additional year of education. That's how I would write that. So the outcome variable is predicted to go up if it's a positive slope. The outcome variable is predicted to go down if it's a negative slope. Confidence intervals then, you can make a confidence interval around the predicted value. So I went ahead and did that for the intercept. And this is the picture that I thought was going to be next like 20 slides ago, and I remember now why it's not next. It's because it displays confidence intervals. So, do you see this shiny, tiny shaded line here around the line, the blue shading? That was built by creating a confidence interval around the predicted outcome given by the regression line. So the software does this for you and it spits out a picture. This is from SAS. Now, one thing to note is the width of the blue shading is skinnier at the middle and it gets wider as you move away. 1 second. Stick time. I brought it. Fulcrum. If you have a slope, where it ends up matters a lot more than where you are in the middle. So the prediction is going to be the most precise from the regression line at the mean of the predictor. In our data, the mean of the predictor was like 13.4 or something. So it's just a little bit ahead of where we centered it at 12. As you move away from the mean, though, what your predicted value is going to be depends more on the exact answer of your slope. A little bit of a slope difference creates more of a difference in prediction at the ends. So what it could be is less precise out here. Now there's also these dashed lines out here. These are confidence intervals for y. Not y hat, but y. What's the difference? What does y have that y hat does not have? E. So taking into account not just the prediction of the model, but how much error wrongness is left around it. Like how far off are the people from the regression line? If we take that into account, that's how we get to these lines out here. So much bigger. All right. 313, that's a great stopping point. Transitioning into effect size next time. Questions before we call it a day? No questions. Should we call it a day then? Yes. Everyone is definitive on that point. We shall call it a day then. Office hours start shortly. I need to get back up to my office, then I'll reopen the Zoom. Thanks for coming, Zoomers, Livers. I will see everyone on Thursday. Take care of yourselves until then. Peace out.
Thank you.